You know, it is a truly universal frustration. You open your weather app, and it knows exactly what is going to happen tomorrow. Like, it promises rain at 3:15 p.m., and at exactly 3:15 p.m., the sky just opens up.
Oh, yeah. It's uncanny.
Right. But then you try to look, I don't know, 3 weeks out, and suddenly that same app is just totally guessing.
Right.
It is throwing out percentages, showing vague pictures of clouds, basically just crossing its digital fingers.
Mm-hmm.
And I always wonder, why is it that our technology is so incredibly precise in the short term, but it just hits this absolute brick wall a few weeks down the line?
Well, the natural assumption most of us make is that it has to be a hardware problem.
Yeah.
We think if we just had better satellites in orbit or more powerful supercomputers or slightly more accurate thermometers, we could push that wall back. We operate under this belief that it is simply a matter of what we don't know yet.
Right, like we just need a bigger engine.
Exactly. A bigger engine, more data.
But today, we're going to find out why that assumption is entirely wrong. We are taking a deep dive into a really fascinating book called Order in Chaos, Poincaré and the Boundaries of Prediction, and this is written by Boris Krieger.
It's such a great read.
It really is. Our mission today is to explore the life of Henri Poincaré, a man who is often called the last universal mathematician, and discover why our inability to predict the future is not actually a failure of our technology. It is a fundamental law of the universe.
Yeah, and what Boris Krieger does so brilliantly in this book is he maps out the critical difference between what we don't know yet and what we simply cannot know at all.
It's the impossible stuff.
Right. We are looking at a permanent, uncrossable boundary in nature. And we inherited this understanding from a man who wasn't even trying to predict the weather. He was actually trying to figure out if the solar system would eventually fly apart.
Which is wild.
Yeah.
But ironically, he started this cosmic journey at the bottom of a coal mine, of all places. So let's go back to September 1879, to the Magny mine shaft in France. It was a brand new, incredibly deep coal pit. But just a month after opening, the air inside caught fire.
It's awful.
16 men died in a massive fire damp explosion. And for those who don't know, fire damp is essentially invisible, odorless methane that just seeps out of the coal, and it is notoriously deadly.
And the terrifying thing about fire damp is the mechanics of how it ignites, because it only burns within a very narrow window of concentrations.
Okay, what do you mean by that?
Well, if there's too little gas in the air, nothing happens. If there's too much gas, the oxygen is choked out, so again, nothing happens.
Oh, I see.
But right in that sweet spot, a single solitary spark from a miner's pickaxe turns a mile-long mine tunnel into the barrel of a gun.
Wow. That is terrifying.
It is.
So enter Henri Poincaré. He was a 25-year-old mining engineer at the time. And he goes down into the burned-out gallery, examines the soot, the debris, the blast patterns, and he actually reconstructs the explosion perfectly from the physical evidence.
He was a genius.
Total genius.
Mm-hmm.
He figures out exactly where the gas came from and how the blast traveled. He essentially solves the puzzle of the past. But then the mining company asks him the big question, which is, can you guarantee this won't happen again?
Mm-hmm.
Can you certify the mine is safe for the future?
And that is the exact moment he bumps into the boundary. He looks at the systems at play and realizes he just can't.
Right.
He tells the company that the ventilation is improved, sure, but he absolutely cannot guarantee the future.
Because of the variables.
Exactly. Because the crucial variables, like exactly how much gas a newly struck rock will release, or the exact millisecond a spark might happen to fly from a tool, they are simply too microscopic and too sensitive to measure and control.
Okay, let's unpack this with a metaphor, because I think it helps. Explaining the past is kind of like looking at a crashed car and seeing exactly why it broke. You can see, oh, the brake line snapped, the tire blew out, the steering column locked. It is a single traceable sequence of events. But predicting the future is like looking at a busy highway and trying to guess exactly which car will crash next Tuesday based on a gust of wind happening today.
That is a highly effective way to visualize it. As Boris Krieger notes in the text, the past is a single realized sequence. You can always narrate it backward because the variables have already collapsed into a single timeline.
It already happened.
Exactly. The future, however, is an entire fan of possible sequences permitted by the rules of physics. And if those rules amplify tiny differences, like a spark hitting a slightly denser pocket of gas, well, that fan opens up faster than any of our measurements can close it.
Yeah.
And Poincaré, at just 25, was already living inside the asymmetry of time that he would eventually prove mathematically.
So if Poincaré realized he couldn't even predict a small, contained explosion in a hole in the ground, How did he react when he was asked to predict the fate of the entire solar system?
Yeah, quite a leap. Seriously. Because that brings us to the King of Sweden's prize, which was exactly 10 years later in 1889. King Oscar II offers this massive prize of 2,500 crowns to anyone who can solve the three-body problem.
Right.
And essentially, the king wanted to know, can you write a mathematical formula to prove that the solar system is stable? Will the Earth keep orbiting the sun safely, or will the gravitational pull of the other planets eventually fling us out into deep space?
It is the ultimate test of predictability. And so Poincaré submits a 160-page memoir. He basically strips the problem down to its absolute core. Instead of all the planets, he just looks at two large bodies and one tiny grain of dust.
Okay.
So say a star, a massive planet, and a small asteroid. And he proves that the formula the king asked for simply doesn't exist.
It just doesn't exist.
Right. There is no simple, clean equation that will predict the solar system's exact motion forever. But he uses a completely new method, looking at the geometry of the orbits rather than their exact coordinates, to show the system is generally stable.
So he still kind of answers the spirit of the question. Yes. He wins the prize, he gets the gold medal, and overnight he becomes the most famous mathematician in Europe.
But then, the editor of the journal publishing the winning paper, a guy named Edward Fragman, starts asking some really detailed questions. He is prepping it for print, and he just can't follow one specific part of the math. So he writes a letter to Poincaré asking for clarification.
And we should clarify that Fragman wasn't trying to tear the paper down.
No, not at all.
He was just being a conscientious junior editor trying to understand a genius's work. But his innocent questions forced Poincaré to go back and look at a foundational assumption he had made.
What was that assumption?
Well, Poincaré had assumed that a celestial trajectory leaving an unstable orbit and a trajectory returning to it were traveling along the exact same curve.
Okay.
It was a totally natural assumption. In the physics of the time, everyone would have made it.
But it was completely wrong.
It was catastrophically wrong for his calculations. And realizing this, Poincaré does something that is almost unheard of in modern academia.
Yeah, he halts the publication, which is crazy because the memoir was already printed and bound.
Right.
He telegraphs the publisher to stop distribution, recalls the copies, and has their entire edition destroyed. And then he pays 3,585 crowns of his own money to reprint the corrected version.
Just to put the financial weight of that into perspective, the prize money itself was only 2,500 crowns.
Oh, wow.
So he paid a year and a half's worth of his winnings just for the privilege of fixing a mistake nobody else had even noticed yet.
Talk about absolute integrity. But this is what the mathematician Jean-Christophe Joukos later called the fruitful error. Because when Poincaré went back and actually looked at what happens when those two curves don't match perfectly, he stumbled into something completely mind-blowing.
Yes. He discovered what we now call the homoclinic tangle.
The homoclinic tangle.
Exactly. When those two curves cross in the math, they don't just cross once and move on. To obey the laws of physics, they have to cross infinitely many times, folding and stretching and weaving into this infinitely dense mesh. Boris Krieger emphasizes a profound point here, which is that inside that microscopic mesh, the future comes completely apart.
Okay, slow down for me here because this is where the math gets intense. How exactly does a mesh of crossing curves destroy our ability to predict the future?
It comes down to decimal places. Imagine two planets starting their orbits just a millimeter apart.
Okay, pretty close.
Right. In a normal orderly system, they would stay about a millimeter apart. But in the homoclinic tangle, that infinitely dense mesh of intersecting forces acts like a cosmic blender.
The cosmic blender.
Yeah, that millimeter difference means one planet might get caught on the left side of a tiny mathematical fold, and the other gets caught on the right side. Fast forward a million years, and the first planet is safely orbiting the sun, and the second has been flung entirely out of the solar system.
Wow. So to know which fate awaits the planet, you would need to measure its starting position to an infinite number of decimal places.
Exactly, and that is impossible. This is the absolute foundation of chaos theory. And the critical takeaway here is that it has nothing to do with randomness.
Wait, real?
Really? The math is completely deterministic. The universe knows exactly what it is doing. The gears are turning perfectly. But because an infinitely small difference in the starting position leads to a massively different outcome, we are permanently barred from calculating it.
Because we can't measure perfectly.
Right. Our rulers and telescopes will never ever be precise enough.
Which brings up a really unsettling thought. If our equations can't map this chaos, and our measurements are never precise enough to guarantee the future. What does that say about the very tools we use to measure reality? I mean, things like space and time themselves. Are our rulers fundamentally broken?
Well, Poincaré started wondering the exact same thing. He didn't just stop at astronomy, he started questioning the very language of science. Boris Krieger walks us through this amazing thought experiment Poincaré came up with called the heated disk to explain this. I want you to picture a finite, flat disk, like a massive coin.
Like a massive coin. Got it.
But there's a specific physical rule here. The temperature is hottest in the exact center, and it drops steadily as you move outward, reaching absolute zero exactly at the outer edge.
And in this world, everything shrinks as it gets colder. So the rulers shrink, the people shrink, their physical footsteps shrink.
Right. Now, put yourself in the shoes of someone living on this disk. You start walking from the warm center toward the cold edge.
Okay.
As you walk, your body and your measuring stick are shrinking in exact proportion to the temperature drop.
So you take a step, but your step is physically smaller than the last one. You measure the distance you've traveled, but your ruler is shorter, so it tells you you've covered a normal distance. To you, it feels like you are walking at a steady pace forever.
Yeah.
You will literally never reach the edge because you just keep shrinking into infinity.
Precisely. The inhabitant of that disk would measure their world and conclude with absolute mathematical certainty that they live in an infinite space with a curved, non-Euclidean geometry.
Wow.
Meaning, the standard rules of flat geometry, like parallel lines never meeting, wouldn't apply to their measurements. But to us, standing completely outside the disk in a warm room looking down on it, we just see a finite, flat circle with a weird temperature gradient.
That is so trippy.
And here is the kicker. Every single measurement the inhabitants take, and every single measurement we take from the outside, will perfectly match our respective theories. No experiment could ever prove which reality is the true one.
Wait, my brain is snagging on this. Is Boris Krieger saying that science is just made up?
Yeah.
That everything is just a game of arbitrary rules and none of it's actually real?
It is a very common trap to fall into when thinking about this, but Boris Krieger makes a very exact distinction here.
Okay, good.
Poincaré wasn't saying science is a fiction or a lie. He was saying that the language we choose to describe reality, like geometry or a definition of time, is a convention.
A convention?
Yeah, we choose it because it is convenient for our perspective. Think about human languages. Speaking French isn't an arbitrary game. It's a real, rigorous language with strict rules.
Right.
But speaking French is not a fundamental truth of nature either. It's an agreed-upon framework.
So the scientific fact isn't the language itself, but whether or not we can successfully use that language to translate reality and make predictions that actually come true.
Precisely. And Poincaré ran into this in his day job, too. He worked at the Bureau de Longitude, dealing with telegraph cables across the world.
Oh, that makes sense.
Yeah, and he realized that our entire concept of simultaneity, the idea that two things are happening at the exact same time in different places, is actually a massive assumption.
How so?
Because to synchronize two clocks in different cities, say Paris and New York, you have to send a signal between them. But that signal takes time to travel. To calculate the delay, you have to assume that the speed of light is exactly the same traveling west as it is traveling east.
But we can't actually prove it's the same in both directions without already having synchronized clocks. Here. It is a circular problem.
Exactly.
We just agreed to assume the speed of light is constant in all directions because it makes the math work cleanly.
But if we are just choosing our conventions of measurement and assuming foundational things to make the math work, we run into a very dangerous problem.
Yeah, I could see that.
How do we stop ourselves from finding patterns that aren't actually there? If you build a framework based on assumptions, you can accidentally manufacture a false reality.
And this leads us to one of the most terrifying traps in human reasoning, which is the prosecutor's fallacy. Boris Krieger details Poincaré's involvement in the Dreyfus affair in 1904, which is a chilling example of this.
It really is.
Alfred Dreyfus was a French artillery captain who was wrongly convicted of treason, and the main piece of evidence against him was a torn note found in a wastebasket. A famous forensic scientist at the time, Alphonse Bertillon, examined the handwriting on the note and claimed he found 13 coincidences.
13 coincidences.
Yeah, 13 specific alignments and measurements that supposedly matched Dreyfus's normal handwriting perfectly.
And Bertillon calculated the odds of these 13 coincidences happening by pure chance. He multiplied the probabilities together and concluded the odds were infinitesimally small.
Almost impossible.
Right. And the court heard this astronomically tiny probability and treated it as absolute, irrefutable mathematical proof of guilt.
But when the case was eventually appealed, Poincaré was brought in as an expert witness, and he absolutely demolished Bertillon's math. Boris Krieger notes two fatal flaws that Poincaré pointed out, and if you're listening right now, think about your own handwriting. The first flaw was that Bertillon only asked what the odds were of finding these patterns if the document was a forgery.
Right.
He completely ignored the baseline. He never asked how likely these same patterns were to appear in perfectly innocent, natural handwriting.
Which is incredibly common. We all have little quirks and repeating distances in our normal handwriting that might look suspicious if you put them under a microscope. But the second error Poincaré pointed out is even more profound. Bertillon only specified the pattern after he went looking for it.
That is the crucial part. He didn't walk into the courtroom and say, I predict we will find these exact 13 specific loops and gaps.
No.
He just scoured the document for weeks until he found 13 things that looked weird and then calculated the odds of those 13 specific weird things happening together.
It is the Texas sharpshooter fallacy.
Oh, I love that analogy.
Yeah, you shoot a bunch of holes in the side of a barn, and then you walk up and paint a bullseye around the tightest cluster of bullet holes, claiming you are a master marksman. If you search any complex data set long enough, you will eventually find a pattern.
You're bound to.
Right. And the odds of finding that exact pattern will always seem astronomically low after the fact, even though the odds of finding some pattern were practically guaranteed from the start.
And this mathematical error isn't just history. It destroys lives today.
Oh, absolutely. Boris Krieger actually mentions a modern parallel in the book, the Lucia de Bert case in the Netherlands. She was a pediatric nurse sentenced to life in prison because a statistician calculated a 1 in 342 million chance that she would accidentally be present for so many hospital deaths.
1 in 342 million. That sounds so convincing.
The math sounded flawless to a jury. But they didn't account for the fact that she was explicitly assigned to work the ward with the sickest terminal children. And worse, they only started tracking her shifts carefully after they already suspected her, selectively choosing the data that made her look guilty.
That is just heartbreaking.
The math was fundamentally biased by the search method.
Why are we so blind to this? Why do we trust these numbers so implicitly when the foundational assumptions are so flimsy?
Well, Boris Krieger highlights Poincaré's brilliant observation about this, using the tuning fork metaphor regarding the law of errors, or what we commonly call the bell curve.
Okay, the bell curve.
Right. Poincaré pointed out a bizarre truth. Everyone believes in the bell curve because experimenters think it's a mathematical theorem, and mathematicians think it's an experimental fact.
So both sides are just blindly trusting the other side's rigor.
Exactly.
The experimentalist assumes the mathematician proved it universally, and the mathematician assumes the experimentalist verified it in the real world. Nobody actually checks the basement to see if the foundation is solid.
And we see the catastrophic results of this blind trust in modern finance, too. Look at the long-term capital management failure in 1998, or the massive mortgage-backed security crash of 2008.
Right, the housing crisis.
Yeah, the financial models assumed that different global markets or housing sectors were independent of each other. The bell curves calculated that a total simultaneous collapse was virtually impossible.
Because they wouldn't all fail at once.
Exactly. But when those small variables stopped being independent and suddenly all aligned in a market panic, the bell curve didn't just get a little bit inaccurate. It became dangerously wrong, making catastrophic events look mathematically impossible right up until the exact moment they happened.
So, if we look at the scorecard here, we have chaotic systems where equations fail completely. Our measurements of space and time are built on chosen conventions, and our statistics are incredibly prone to human bias and manufactured reality.
It's a bit bleak.
It is. What do we do when the traditional math just completely breaks down? How do we move forward?
We do what Poincaré did. He didn't just give up when he hit the boundary. He invented an entirely new way of looking at the world.
Okay, how so?
When he couldn't solve the three-body problem with a formula that told him exactly where the planets would be, he changed the question entirely. He abandoned the need for exact coordinates, and he started asking about the overarching shapes of the solutions. He invented analysis situs, which we now call topology.
Topology. Okay, this is the famous field of math where a coffee cup and a donut are considered the exact same thing, right?
Yes, because in topology, distance and rigid measurements don't matter at all. The only thing that matters is connection and continuous structure.
Okay, explain that.
If you imagine a coffee cup made of soft clay, you can stretch and mold and squish the cup into the shape of a donut without tearing a new hole in the clay.
Oh, because the handle of the cup just becomes the hole of the donut.
Exactly. Topology is about understanding the fundamental properties of a space rather than obsessing over its exact, unpredictable coordinates.
And as he was building this entire new branch of mathematics, Poincaré proposed a conjecture about three-dimensional spaces. He essentially wanted to know if a specific test, like checking if every loop you draw in a space could be shrunk down to a single point without catching on a hole, was enough to prove that the space was structurally a sphere.
Right.
But in 1904, to test his own limits, he built a mind-bending counterexample to his own theory.
The Poincaré homology sphere, which is often visualized as a dodecahedral space.
But my brain just broke a little bit reading about this. A 12-sided room. How does this even relate to predicting the future?
It relates to how we define the shape of our universe when our standard measurements fail. Imagine you are floating inside a 12-sided room. But the rules of this space are non-Euclidean.
Okay.
If you float straight through one of the walls, you don't hit a boundary. Instead, you instantly reappear coming out of the opposite wall, slightly rotated.
Oh, wow.
It is a finite space, but it has no edges. You can travel forever and never hit a wall, yet the volume of the space is limited.
So he invented a mathematical room that basically loops back on itself.
Yes, and the genius of it was that this bizarre looping room passed all of his early, simpler topological tests for being a sphere.
But it's a 12-sided looping room.
Right, it absolutely is not a sphere. By building this impossible room, Poincaré proved that his early rules weren't strict enough. It forced him to revise his question, leaving behind a final, incredibly difficult conjecture for the mathematical world to solve. A question that sat there unsolved for 99 years.
Until 2002, when a Russian mathematician named Grigory Perelman finally proved it. The Clay Mathematics Institute had offered a $1 million Millennium Prize for the solution. Perelman proved it, the entire global mathematical community spent years verifying it, and then Perelman famously refused the $1 million.
I really did.
He just walked away from it.
And Boris Krieger highlights a beautiful poetic symmetry in that conclusion. Think back to 1889. Poincaré paid more than his royal prize money out of his own pocket to fix his own mistake, prioritizing the truth of the math over the award.
Right.
More than a century later, Perelman refused a fortune for solving Poincaré's leftover question, arguing that the prize structure was unjust and didn't properly credit the earlier mathematicians whose work he built upon.
That's amazing.
Both men, separated by a century of chaotic history, prioritized the absolute integrity of the math over the credit and the cash.
So if we pull all these threads together, what does this all mean for us? We have traveled from exploding coal mines to the edges of the universe to 12-sided looping rooms. Why does all of this matter to us today, to someone just trying to navigate a world full of data and predictions?
It matters because it fundamentally changes how we view our tools. It teaches us how to react when we hit a wall. Finding a boundary isn't the end of an inquiry. Usually that's exactly where the inquiry starts paying off.
How so?
Think back to your weather app frustration at the beginning of the deep dive. Because Poincaré proved that we could never perfectly predict the long-term future of a chaotic system, meteorologists eventually stopped trying to build a single godlike equation for the weather.
Oh, because they knew the homoclinic tangle would just tear a single prediction apart anyway.
Exactly. Instead of fighting the chaos, they embraced it. They invented ensemble forecasting.
Ensemble forecast.
Yeah. Today, they take a weather model, tweak the starting temperatures and wind speeds by those microscopic fractions that Poincaré worried about, and they run the simulation 50 different times simultaneously.
Ah, I see.
They stopped asking the machine for a single fake prophecy, and they started asking it to show them an honest fan of futures.
So if all 50 simulations show rain, I should definitely buy an umbrella.
Yeah.
But if they spread out into 50 totally different weather patterns?
Then the atmosphere is highly chaotic that day, and the most accurate scientific thing the meteorologist can tell you is the exact percentage of that spread.
So that is why your app gives you percentages 3 weeks out. It is being honest about the limits of our knowledge.
Exactly.
Which brings me to a final, really provocative thought to end on. Something else from Boris Krieger's book that I simply cannot stop thinking about. It is his take on the concept of chance itself.
Ah, the roulette wheel.
Yes.
Think about a casino roulette wheel. It is a physical object made of wood and metal. It perfectly obeys the classical laws of gravity, friction, and mechanics.
All right, there's no magic happening.
There is absolutely no magic happening when the dealer spins the ball, yet we universally call the outcome random. Why do we do that?
Because the outcome is determined by a cause so microscopic, like a tiny variation in the twitch of the dealer's wrist or a microscopic speck of dust on the wooden track, that we simply cannot measure it in real time.
Precisely. Chance, as Boris Krieger points out, isn't some magical, mysterious force of the universe injecting randomness into our lives. Chance is manufactured right at the boundary between a complex physical system and our own limited precision.
Wow.
The chance isn't inside the roulette wheel, the chance is inside us.
That really makes you rethink your whole day. Next time you open your weather app or you experience a run of seemingly bad luck or a project at work derails out of nowhere, you have to ask yourself, was it truly random? Or was it just a variable, a tiny initial condition that you simply didn't look closely enough to measure?
It is the ultimate lesson we inherit from Henri Poincaré. The universe knows exactly what it's doing. We just have to be humble enough to accept where our vision blurs.
And maybe that's why predicting the weather next Thursday will always be a little bit of a gamble. It is not a broken thermometer. It is just the beautiful, chaotic math of the universe doing exactly what it's supposed to do.